Okay. Alright, I figured out what happened with this problem. I guess when I was typing the question in, I messed up the sentence. So 2 and 4 have twice the mass of 1 and 3. And you can see that from the diagram. These are 2m, and then these are just 1m. Okay, so I just messed up when I retyped this in from the book. There's a problem book I got this from. So 3 and 4 still have twice the spring constant. And we can see that as well. Here's 2k and 2k. So what happens is 2 is going to have the greatest period value because it's 2 times m over k. Okay, so it's the greatest. And then 1 and 4 are actually equal because these 2's are going to cancel out. So 2 is greater than 1, which equals 4. And then 3 is the last one because it's got a 2 on the bottom here. So that's going to be answer choice B. Okay, so sorry about that typo. I messed that up. Too many 1s, 2s, 3s, 4s. Okay, so then same problem. Which statement is true about these oscillators? Okay, so we've got some different statements here. And again, I would discount anything that includes something that's not relevant. So increasing gravitational field strength, that's not going to change the period of these mass on the springs because that is not part of this equation. Even though these are hanging, that doesn't have anything to do with the period. Okay. Increase in air density, that one doesn't even really make sense. Increase in the amplitude of vibration will have no effect. That's actually the correct choice because remember, one of the things about simple harmonic motion is that amplitude does not have anything to do with period. And that's true both for mass on a spring and for pendulums. Okay, so we've got a spring with a given spring constant. It's attached to a block with a given mass, and then that's attached to a wall. So this block is sliding. When the block is at 0.75 meters, the spring is at its unstretched length. So that's its equilibrium position, is 0.75. From which of these positions can the block be released and have a maximum acceleration with this magnitude? Okay, so what we're looking for here is a position or displacement information. So let's use our restoring force. Our spring force is minus k times, this is really delta x, okay, equals m times a. And we're going to solve for this. Okay, so for an acceleration value of 20, what does this this displacement have to be? Or what can it be? Okay, so minus 100, that's my spring constant, times delta x equals 0.5 times 20. I'm going to solve that for delta x. Let me do that real quick in my handy dandy calculator. Oops. So I'm going to get 0.10 meters, basically. Is that right? Yeah. Hang on. Sorry. My brain's not working yet. 0.1, yeah, that's what I thought. Okay, so 0.1 meters or 10 centimeters is my displacement. So that means that I am being displaced 0.1 meters from this position, okay, when I have an amplitude value. So really the only choice from these is this 0.65, because that's 10 centimeters or 0.1 meter off of that. So that'd be like me compressing it in another, basically 0.1 meters. That would give me my restoring force, trying to get it back to equilibrium, and an acceleration value going along with that force of 20 meters per second per second. Okay. Okay, this one's kind of wordy. We've got a block attached to a spring on a horizontal surface. When it's at its max displacement, meaning it's at an amplitude value, the force exerted is Fa. And when it's at equilibrium position, the force exerted is Feq. Okay? And so which of these compares these correctly and provides a valid justification? So basically we know, because this is in simple harmonic motion, that when we're at a maximum displacement, we're going to have a maximum restoring force value. Okay, so that Fa is going to be a maximum there. When we're at equilibrium, we have a 0 restoring force value because we're at equilibrium. The restoring force wants to bring us back to equilibrium. Okay, so we know that Fa has got to be greater than Feq, because Feq should be 0 at the equilibrium point. So there's two choices where Fa is greater than Feq, and then let's look at what the explanations say. So this one says speed of the block is at a maximum when the displacement is at a maximum, and 0 when the displacement is 0. And that's actually not true, because our speed is going to be the greatest when we're at equilibrium, because that's where our kinetic energy is the greatest. And then let's see, this says force is 0 at equilibrium position and a maximum at maximum displacement, and that's the best explanation here. Okay, even though it's kind of wordy, these forces are not going to be equal at those 2 points. They can't be. If you're in simple harmonic motion, you have to have a restoring force at your maximum displacement, and then that restoring force value and the acceleration value are 0 when you go through equilibrium. So, okay, I'm going to stop there. I'll try and, I got 2 or 3 more questions. I'll at least post a key to those. I'll try and video them if I can, but at least I'll have the full key posted as well.